Okay, we're back. We're doing some electromagnetism, and this tends to be one of the most challenging types of problems that you can get in E&M, at least for our level in the Physics C course. This is Biot-Savart, this is magnetism, and we're trying to figure out magnetic fields due to currents. Okay, in particular, these are currents in wires that actually do have ends. Unfortunately, because we start to lose some of the symmetries that we get when you have a so-called long wire with a current, that's when we can use Ampere's law. In this case, Ampere's law is not going to work for us. Okay, when you have ends. Things get weird when you have ends. So Biot-Savart, this is the rule, this is the law that we have that will find magnetic fields exactly. Okay, and it can be for multiple wires, multiple currents, multiple charged particles flying around. This is the real deal. So it's our job to try and figure out, in the case of currents, the integral that we need to use that would solve a particular problem. Unfortunately, there's no one integral fits all. We have to kind of construct these things based on the problem at hand. So every problem's a little bit different. So let's work through an example. I'm going to show it down here. And basically we have our two wires. One's going vertically, one's going horizontally. You've got these two different currents, I1 and I2. And there's a point out there in space, point P. It's halfway down the vertical wire, and it's at the end of one of the other wires. And we're trying to figure out what exactly the magnetic field would be at that particular point. Okay, so what we're after is how to set up an integral, okay, for each of these wires. Because we have two currents, we're going to have two different magnetic fields. Not only that, but if you look at the direction of the currents, let's say for current 1 in the vertical wire, if we do the curly right hand rule, that is, if we take our right hand and point our thumb down in the direction of the current, our fingers are going to curl in a way where the magnetic field coming from current 1 will be out of the screen at point P. Now if you look at current 2, which is going to the left, take your right hand, take your right thumb and point it to the left in the direction of current 2. Curl your fingers around, and if you're above that wire, its magnetic field is actually into the screen. So not only do we have two different magnetic fields, they're in opposite directions of each other. So in other words, to find the total field, we'd have to subtract those two. I'm not going to use any numbers. I'm going to keep this symbolic, so we can try to figure out how to set up an integral using the Biot-Savart rule, which is right up here that I just kind of circled. It's very similar to what you have for point charges. And in fact, it sort of tells you how to do the problem. We're going to try to break a current up into small pieces. Basically treat them like they're little moving point charges. Okay, and realistically that really is what a current is. So it kind of makes sense to take that approach. It has the same basic structure. Notice there's a cross product in there. The cross product is what is the math that kind of sets up these circulating magnetic fields that go around the currents. Okay, that's why we need that curly right-hand rule to figure out the directions of the magnetic fields. So let's start with that vertical wire. Okay, wire 1. Okay, now this thing, what this basically tells us to do, Biot-Savart, is to take a little piece of the wire, a little blue point up there. It has a little bit of length to it. That's the dl that's in the Biot-Savart rule. There's a certain distance that goes out to the point that we're trying to find the magnetism. Okay, so now this vertical distance from the axis there, I'm just going to call that y because we're in y direction. And now the horizontal distance out to the point is L2. That's the length of that bottom wire. So what we can do is at least figure out, based on the geometry here, that the distance from that little piece of current out to the point that we're looking at, using Pythagorean theorem, is going to be y squared plus L2 squared. Okay? So the little bit of magnetism that that little bit of current is making, okay, according to our rule, we've got some constants. We've got the mu naught over 4 pi. We've got the current, which is current 1, times that little bit of length, crossed with r hat. Okay, now this is where we have to be a little bit careful. The r hat is a little unit vector that points from the piece of current towards the point that we're trying to find the magnetism. Now there's an angle there, as you can tell from that big triangle. There's an angle between the current and that radius line. I'm calling that theta 1 up there. Okay, to do a cross product, we have to account for the sine of that angle. Now the magnitude of our hat is just 1, so that's never going to mess up your calculations. But we do need the sine of the angle that's up there. And that's all going to be over r1 squared. Okay, so that little bit of magnetic field, if we kind of simplify this a little bit, let's substitute some things in here. We've got current 1. You know, because that length is in the y direction, I'm actually going to rename the dl. Let's call it dy. The magnitude of r hat is 1. Now, from our triangle, the sine of that angle is looking like it's going to be L2 over the hypotenuse, which is r1. The whole thing is over r1 squared. Okay? So in the parentheses here, that's the sine of that angle. Make sure that makes sense based on the picture that we have, our triangle up there. Okay? Now, how do you find the total magnetic field due to current 1? Well, we have an expression here now from the geometry of the problem that gives us the little magnetic field from a little piece of the current, a little piece of the wire. If you want to get the total field, you have to add up all these little fields. That's what integrals do. Okay, so we have to integrate what we just came up with. We're going to have current 1 times dy. L2 is just a number. That's the length of the other wire. And it's going to be over r1 cubed. Okay, but now r1 is that square root. And that's the Pythagorean theorem that we set up. So just to get this in kind of a final form, we have I1 times dy times the length of wire 2 all over r1 cubed. So that's going to be y squared plus L2 squared to the 3/2 power. Now the last piece that we need here are the bounds, the limits on this integral. We want to make sure we go from one end of that wire all the way to the other end of the wire. So it's kind of like going from negative half the length, so negative 1/2 of L1, to a positive L1 over 2. That'll add up all these little contributions. So that's the weird looking integral. Why is our variable there? Okay, that's the thing that changes from point to point. It's that y message, that y distance. Okay, so this is the integral to find the magnetism just from that vertical wire. But that's only half the problem. Now we have to do a similar thing for wire 2. That's why these things can be very tedious. We're going to use exactly the same process. And I'm going to use this little space up here. So how do we find a little bit of magnetism caused by current 2? Okay, so I have to take a little piece of the wire, and that little length I'm going to call dx because we're in the x direction. Now that has a distance r2 from the wire to the point that we're looking at. And so now if we think about that cross product, we know the current's going along the wire. Our hat points from the piece of the wire that we're focused on up to the point. And so there's another angle here. That's angle 2. Okay? So what this is going to look like, using our Biot-Savart rule, is our constants. We have current 2 now. The length of that little chunk is we're calling dx. Now the x is going to be our variable now. Well, let's see. The other sides of this triangle, this is going to be half of L1 in the vertical direction, and our horizontal leg is just x. X is our variable for this one. The magnitude of our hat is just 1, and we're going to need the sine of angle 2. That's how we do magnitudes of cross products. And that's all going to be over r2 squared. Okay, now if we substitute in, very similar to what we just did, notice that the sine of angle 2 is L1 over 2 all over r2. So if we substitute all of this in, we know that we're going to have to integrate all these little magnetic fields to get the total B2. We've got our constants, we've got current 2, we've got dx. We're going to have L1 over 2 in our numerator, and that's all going to be over R2 cubed. R2 is x squared plus half of L1, half of the other wire's length, squared, and it's all to the 3/2 power. Now, what should the bounds be on this? This is what tends to change when you have these wires. It all kind of depends on where the point is with respect to your wire. Now in this case, one end of the wire is x equals 0, the other end of the wire is its length, L2. Okay, so if we go from 0 to L2, that would add up all of these contributions. Okay, that's how we find the strength of the magnetism caused by wire 2. Now we also know the directions. We know we're going to have to subtract these things. So your total magnetic field, let's say if we were to say that the positive direction is out of the page, it's usually your z-axis, it's going to be B1 minus B2, since they're in opposite directions. Now again, I don't care right now what the final solutions look like for these integrals. Okay, that's math. I want to make sure that the focus of this is on the physics of it. How do you actually get this crazy looking expression here? Use that for a given picture. It gets messy in a hurry, as you can tell. But with these straight wires, we can set up triangles. We can use Pythagorean theorem. We can get these distances and sines of the angles, and you get some just pretty messy looking integrals. Okay? But it's doable, and it takes practice like anything else. These aren't obvious, I admit that, but with some practice you can start to get the hang of setting these integrals up from scratch. They're all kind of done the same way in the end. Usually the thing that changes most are what you have as the limits on your integral. Okay, these bounds. And that really depends. It's going to vary from picture to picture. I hope this helps. I hope this takes a little bit of the fear out. Replay this video if you need to, and go over the setups of these integrals again if it's not clear, and you'll get it. Until next time, see you later.